Welcome everyone. A few years back, when I've heard for the first time about VEX, I had a look what it means, and I said, well, in the embedded field, we are basically doing it for years already. But this talk is going to be a story about the experiment when we wanted to output the standard VEX from our embedded software. So, who I am? My name is Marta. I've been working in the open source for the last 20 years. In a very big part of that, working on security, including security processes, tooling. This is what we are talking about today. And in the recent times, also a lot about the Cyber Resilience Act in Europe, and I have a second talk about this subject tomorrow. I've recently founded a company working 100% on open source security, and this talk shows my own opinion and is not a reflection of an agreement in any project, including the Yocto project that I will be covering a lot. So, first, what is the Yocto project? I would bet that most of you use devices that have been built using the Yocto project, but you may be not aware. The Yocto project is a way to build your own Linux distribution, and it's mostly used by embedded vendors to build distributions that are running from everything from your smartwatches to your fridges, network routers, industrial machines, and you can't really imagine what. The advantage of the Yocto project is that it's very easy to extend for your hardware. So you can easily add support of everything that you need, and it's a de facto standard for building custom Linux distributions. It's an open source mix of MIT and GPL, and it's a project from the Linux Foundation. So you mostly own at least one device that have been built using a Yocto project, and we are going to discover a little bit more how we build embedded software with it. So there are two important concepts before we get further. In the language of the Yocto project, a recipe is a way to build one software package. It may be a compiler, it may be a library, it may be an application, but it's one software package. The recipe is giving instruction on how to build it, points to the source code where to get it from, and supports all of the programming languages and ecosystem that you can imagine, starting from assembly in C to Java, Rust, Go, Python, Node.js, and everything else in the middle. Then you have something called layers, and layers are collections of recipes, usually having some common purpose, either to support some common hardware or for a specific functionality. So here at Vulkan, an example, meta security, that is bringing in security tools that embedded developers may want to use in their project. Now, how it looks like when you are building firmware for a device. At the first glance, you take the official layers from the project, that they have recipes, you combine them together, and you build your device firmware. That's the theory. The practice is a little bit more complicated because you will use the standard layers, but you will also use layers specific to your hardware. They may come from your vendor, and the layer from the vendor can modify some of the build recipes from the main layers. And it doesn't stop here, because device vendors also add their own modifications, and they add their own layers for some specific software, for example, for the application software that is running on your device. And all of those layers can be modifying all the elements. So you may be asking a question, what is the link of all that with vulnerability management? And the link is that when we have a system image, we want to check it for known CVEs. And the Yocto project has a tool for that called, quite originally, CVE check, that is used to check the whole composition for known vulnerabilities. It's pretty fast, it's not adding much to the build time, and it's using all the metadata that we have from the whole bit system to do the scan. And it has some nice features, like you can override some information in the scan, a little bit of that later. And it supports the fact that some of the recipes hold specific patches to fix given CVEs. Of course, as for every tool, it has some limitations. So like most of vulnerability scanners those days, it's using package versions only, and it's not testing if the vulnerability is actually present or it's reachable in the given code. It doesn't support embedded code. In the embedded world, it's pretty common that some vendor copies some library in the package. And this case isn't handled. And as of today, the Yocto Project CVE check is using only the NVD database. If you are interested, I'm giving a link in the slides to the whole presentation I had on the tool. But let's go to practice how a recipe with additional vulnerability information can look like. This is a real example of a grub2 bootloader recipe, quite recent. From the kernel main version, at the top you have summary description. What is interesting is the part with SSURI, where you have all the components that are needed to build the actual bootloader. The first element is the main source code that we download at the build time. Then you have some patches that are specific to the embedded field that are not in the upstream grab. But then what you get a bunch of files with strangely familiar names, like CV 2024 45781.patch. What's that? Those are patches to be applied on the grub source code to fix that given CV. There are many, because in this specific example, the grub project doesn't have a policy of stable versions. So if in a device that is on the market, you need to grab all the subsequent patches and apply them to your release version. And for grub, it can really get quite long. The CVE checking in the Yocto project is taking that into account. Those files are named in such a way on purpose, because that information is used during the CV scan. So what we are getting, that we have a grub version 2.12 that has normally all of those vulnerabilities, but they are being fixed because of the patch files that we have and the patches applied. So that's one of the features that we have in the project. The second feature is that we can override some of the results from NVD scan. And I've collected a few examples that are quite representative of what has been put in. The collection dates is quite a long work. So, for example, we have the first CVE just saying that the entry in the in the NVD database is incorrect. So this CVE doesn't apply. We have quite many of that, especially with the NVD problems, as they stopped accepting patches or delayed accepting patches to entries. There are quite many of those, and quite many for other vulnerabilities also. The second example, not applicable platform. The Yocto project is used to build Linux distribution, so issues that happen on Windows only, they do not apply in our case. So the product doesn't have that vulnerability. It's not exploitable. And then the third example, even more complex. It's not applicable because of a configuration. The vulnerability could be exploited, but only if there's a specific ownership of a specific file, and the default configuration that is shipped for this package has a different configuration, so the vulnerability cannot be exploited. And that's only the beginning of all the entries that we have around those CVEs. So it does look like a VEX, right? A little bit. In our case of embedded products, a small embedded product is at least 200 packages. So we absolutely need the whole thing automated, otherwise it's very hard to handle. And manual touch is possible, but really only for a limited number of entries. So we tried to output a standard VEX from our tooling to be able to use it, reuse it, and mix with results from other software. And the good news is that we can actually generate quite many complete VEX entries from the data that we have. But not everything fits any VEX standard that we can put our hands on. So we need at least non-standard extensions to output all that we have. For example, there is no VEX statement for the NVIDIA database is wrong for this entry. There's a status for disputed in the CV entries, but it's quite complicated to expose it in VEX. And we also have a situation like this is an abandoned project. There's not going to be a fix. And this is also not directly possible. And there are more cases like that we cannot actually expose. Then what we were looking for and what would make sense is to have at least 2 levels of assessments. Because we have generic assessments that are always true. So like fixing NVD entries, and that could probably all go to CV enrichment. And then we have assessments that are specific to products, to a specific build configuration, and this is more similar to a typical VEX. Currently we have the one set of metadata that is describing everything, because we couldn't find a good format to express everything else. And then we have some interesting open problems. As layers from vendors, from device manufacturers. They can modify the build configuration. They theoretically could modify also the VEX statements that have been created in the main layers. For example, in the case of a configuration option, if there's a statement that this configuration option is disabled by default, and the package doesn't have a vulnerability, someone enables that option in their own layer in the same package, and the statement it doesn't hold anymore. And of course, people can add patches. Those patches may have additional vulnerabilities. They may be unblocking some other vulnerabilities. So there are more interesting open questions like that. How do we handle that inheritance? And I do not have a good answer for that. So the current situation is that we do generate VEX today. It's not a mainline option of the Yocto project, but we are advancing. The current VEX output is based on OpenVEX, but it has some additional statuses that we had to add, and it's a part of a bigger software working on generating CV-rated information outside of the build itself. The code is open source, and you can have a look if you are interested. And we are really looking for more standard solutions to deal with the problems that we have seen. Embedded vendors will quite likely need to merge SBOMs and VEXes, for example, for multiple processors that they have in one product. So it'd be good to have a consistent set of formats so that this merge is really possible. And that with additional extensions and additional statuses, that it's not that easy as it would ideally be. So this is the end of the presentation. We've managed to generate VEX from all the metadata that we have. That's pretty nice. And we are looking forward into finding solutions on how to fill the missing gaps, how to add those additional statuses, how to easily do the vulnerability enrichment that is necessary in most cases. And I'm really interested to have a discussion about how to do that. On this slide, you can find my contact information. You can contact me by email, by LinkedIn. There are many other ways. So if there are questions in the room, I would be really happy to take them.
Questions in the Discord server. So the first question is, please define standard VEX, CSAF VEX, Cyclone DX style VEX, Open VEX.
When I was talking about the VEX as in this presentation, as mostly in general, we have looked into multiple standards more in details in CSAF and in OpenVEX, and both of them didn't have all the statuses that we would ideally have. We haven't looked into all the other formats, but I would assume that will be similar. If there's a format that has all of those statuses, I'm absolutely ready to have a look. We do not have strict requirements of which format it is. It just has to be a standard format.
We have another question. Where should or could a proper VEX specification standard live?
Where it should live? In my opinion, as most of the VEX standards, as they are, it should be open source with open source tooling so that everyone can study it, can use those tools, and if they want to do conversions between different formats, as it's today between CSAF, OpenVEX, the VEX of SPDX3 and other formats, so that people will be able to do that. But me personally, I think that at this moment we have enough of VEX formats, and that would maybe a good moment to unify to the same to one format that fits all the requirements.
One more question. From your experience, are there any changes would you like to see in VEX?
Yeah, it would be good to for most of the fields that are in the formats. It was pretty easy to generate it, and it is quite reasonable. However, in many standards, there are fields that contain important information but are not totally machine readable, contain basically text. And for us and machine processing, we really prefer machine readable fields, enumerations of different situations, so that we can then use it in processing. In the embedded field, people are really asking for completely automated solutions. Many product manufacturers, they do not have basically security teams, so they are not able to have people filling entries manually, especially for hundreds of packages that they have.
Hi, Marta. Question from Silva, living around Grenoble, by the way. Just a question. You mentioned the fact you are looking for like solutions, tools to merge VEX results from various tools. Can you describe a little bit more like this use case? My understanding is perhaps you're using different tools which are able to produce this VEX document, and the idea behind is to merge, deduplicate, whatever, the information from these various tools. Is that correct?
Yeah, in the embedded field, quite often one device has multiple processors. And for those processors, when you build software, you usually use different tool chains. So you will quite likely end up with different SBOMs and also different VEXs. It may even happen that you will end up in different formats from each of those processors. There is basically a need to be able to convert from any format to any format so that you can do merging.
So challenges are around the fact standards are different plus multiple files.
Yeah.
Okay, thank you.
We have another question. Why does Yocto care about VEX? Are Yocto-based distributions pushing for VEX?
There are people who are asking me about VEX to output it. I can tell you that I've been working on the CV checking code for the Yocto project for the last few years, and there's just more and more interest in this, in the code itself, in the correctness of results. So there are more and more companies that want to output correct information about the vulnerabilities, known vulnerabilities that they have in the embedded code for the regulatory reasons and for other reasons. The embedded field doesn't have really much knowledge about VEX itself yet. They are currently mostly about generating S-bombs and eventually generating CV-rated information. But for me, that's a very likely next step. And in many cases, they do VEX-like behavior, but it happens mostly in spreadsheets when customers ask. So moving to a machine-readable format, maybe that would be a good idea. That will be my answer.
We have a follow-up on the question about where VEX should live. So they're asking, is there any specific preference for ETSI, ISO, OSS, IETF, OpenSSF, or something independent?
On open source place and the specification for the embedded crowd, it must be open source, so you don't need to pay to access it. That already removes some of the organizations from the list. Other than that, I do not have a strong preference as long as it stays open source.
I'm in the room and I missed most of the first half, at least, of your talk, so apologies for that. But from your experience, are there changes you would like to see to VEX? It seemed like there might be, but I didn't quite catch that.
Yeah. So there are two main aspects. First is the expressions of vulnerability statuses. It doesn't allow to express everything that we would like to, and I have examples to share with everyone who wants to discuss that. And the second less important issue that we had is that some fields are designed for human readable content, while the information is important and it's not available in a machine readable field at the same time. Can show examples also of that when we have a time to talk in more detail. So for me, those are the two most important issues. Other than that, at the basic level, all of the VEX formats that we have had a look, they fulfill the role just fine.
To be honest, I don't understand VEX that much. It's something I learned today. So my question is that can Yocto be used like a debugger for something, let's say baseband? Because like you have a PhD in telecom, and so can it be used as a GDB for something like baseband? Because it's gets very complex when you debug something like that.
You can definitely create a diagnostic hardware device, like telecom protocol monitoring or something like that with the Yocto project. But you would probably need to develop a little bit of software to do the actual analysis, but everything else that you need to create that device, you would probably find inside.
So is Yocto would consider going in that direction towards the open source development of tools like that?
This is up to the community, because people contribute recipes to build the tools that they want to. So if there is interest, the people interested, then that's going to happen.
I think that's all we have. we don't have any more questions, and we're right on time. Thank you so much.
Thank you.